A vacuum cleaner does not project a pulling force from the nozzle. Its motor-driven fan lowers pressure inside the air path. Atmospheric pressure in the room then pushes air and dust into the nozzle. But if all collected material travels directly to one filter, dust rapidly covers the pores and airflow decreases. A cyclonic vacuum removes much of the particle load before air reaches the fine filter. It does not begin by screening every particle through a membrane. It makes the air rotate and exploits the fact that particles cannot change direction as easily as the surrounding gas. Yet separating smaller particles generally demands more intense swirling flow, and that swirl consumes some of the pressure difference the fan worked to create. Follow the air path from the floor. The cleaning head forms a restricted opening so air velocity can entrain debris. Ducting carries the air particle mixture to the separation bin. A coarse screen or shroud prevents hair and large debris from entering the smaller cyclones. Air enters each cyclone tangentially, rotates around a cylindrical or conical wall, reverses direction, and leaves through a central outlet. Separated dust falls into the collection bin. Air leaving the cyclone still passes through one or more filtration stages, because very fine particles can escape with the upward vortex core. The flow then passes through the centrifugal fan, driven by a high-speed motor, and leaves through the final filter or exhaust path, depending on the architecture. The entire path must remain sealed. A gap at the bin lid, a gasket, or a hose joint gives air an easier route. The motor may still run at full sound and speed, but pressure difference at the cleaning head falls, because flow is no longer forced through the intended path. The brush roll, where fitted, adds another function. It agitates carpet fibers and loosens particles so the airstream can carry them. It does not replace airflow, and airflow does not replace agitation on every surface. The cleaning head must combine mechanical contact with an air path that does not seal so tightly that useful flow collapses. Dust and air enter together but cannot follow the same motion equally well. Air is light and changes direction readily. A particle has inertia. When the gas curves around a cyclone, aerodynamic forces try to pull the particle onto the curved path. Larger or denser particles respond less easily, migrate toward the wall, collide with it, lose energy, and descend toward the bin. Fine particles are more difficult. Their mass and inertia are low, so they follow gas streamlines more closely. Turbulent motion can move some of them into the rising inner core. Material that has reached a wall can also be re-entrained if flow inside the bin is poorly managed. A cyclone is therefore not a perfect separator. Higher flow speed can increase centripetal acceleration and reduce the particle size separated effectively. But fast flow, abrupt direction changes, and multiple cyclone stages all produce pressure loss. If too much pressure is consumed spinning air inside the body, the nozzle loses its ability to collect material from the floor. How can the machine balance particle separation against useful cleaning airflow? Particle behavior also changes with shape. A compact grain, a long fiber, and a light flake of the same mass do not experience drag in the same way. Hair can wrap around a shroud instead of behaving like a spherical particle. Real household dust is therefore a mixed engineering load, not a single calibrated powder. A cyclone develops two main flow structures. An outer vortex rotates near the wall and travels downward. Near the lower region, most of the air reverses direction and forms an inner vortex that rises toward the central outlet. Particles driven to the wall must lose enough momentum and leave the energetic flow region before the inner core carries them upward again. Geometry controls this balance. Body diameter, cone angle, inlet size, vortex finder length, and flow rate. A larger primary separator can handle fluff and coarse debris at moderate pressure loss. Smaller cyclones use a smaller turning radius and can produce greater angular motion, improving separation of finer particles. A multi-stage system may therefore use a large chamber for hair and heavy debris, followed by an array of smaller cyclones. Even a strong cyclone array does not eliminate the final filter. Cut size is not a rigid boundary. Separation efficiency changes across particle size, density, and flow conditions. Particles below the effective separation range still require filter media. The cyclone reduces the dust mass delivered to that filter, helping its area remain open longer than if it received the entire debris stream directly. The motor and fan must be matched to the resistance of the whole system. High sealed suction does not necessarily mean high working airflow. High free airflow does not guarantee the ability to lift particles through a real cleaning head. Useful performance occurs at the operating point where the fan, ducts, cyclones, filters, and nozzle reach a common balance. As resistance rises, the operating point moves along the fan curve. Airflow usually falls, local cooling conditions can change, and particle transport through long ducts weakens. Designing for only a clean, empty machine would ignore the state in which people actually use it, with dust in the bin, material on the filters, and bends in the hose. As the motor turns, the fan reduces pressure inside the machine. Room air pushes debris through the nozzle opening. Inertia, collisions, and airflow carry the particles into the duct. Large debris slows in the primary chamber and enters the bin. Air containing finer particles divides among the cyclones. Each cyclone converts part of the pressure difference into swirling motion. Particles with sufficient inertia move toward the wall and descend. Air reverses, rises through the central core, and leaves the separator. A filter then retains particles that remain before air passes the motor or reaches the environment, depending on the design. Seals force the flow through this complete sequence. When the bin is overfilled, the shroud is wrapped in hair. Cyclone passages collect dust, or the filter becomes loaded. System resistance changes and performance falls. No controller can compensate indefinitely for a blocked air path. Preserving airflow requires separated dust to leave the active vortex region and the filters to remain permeable. Emptying the bin before debris reaches the cyclone outlets protects more than storage capacity. It preserves the quiet region in which separated material can settle. If that region fills, rotating air can interact with the collected mass and carry particles back toward the active flow. Separation and storage, therefore, have to be designed as one system. Filter placement protects different targets. A pre-motor filter prevents escaped dust from reaching the fan and motor, while a post-motor filter captures fine material associated with the exhaust stream. A fully sealed machine must make all exhaust pass through the intended final medium. A high-grade filter has limited value if air can leak around its edges. A cyclonic vacuum cleaner operates through controlled pressure difference and particle inertia. The fan creates airflow. The nozzle collects debris. Cyclones curve the flow so dust migrates toward their walls. The bin retains separated material, and filters capture what remains. Arrays of smaller cyclones improve fine particle separation, but impose additional pressure, lost. The cyclone's real value is not the complete removal of filtration. It prevents most of the dust mass from reaching the filters, allowing airflow to persist longer in a machine that must account for every pascal of pressure.